This is the last of the 3 videos. This is mainly just going to be notes for you to write down. We're done with the proof, so we don't have to write down notes in class, and we can start applying this to free responses. Now, the proof was pretty involved here, and it looks a little bit intimidating with all this notation. The main thing that we found, however, was that this is the 3rd and last video for error approximation. This is mainly going to be just a few more notes for you to jot down, so we don't have to do it in class, and in class we can start off right away with applying this to free responses. Because remember, the free responses we did in class, we left off all the error problems, mainly because they were all Lagrange. So let's take a look at what we have here from video 2. We went through this long, complicated proof, and we ended up with f of x is equal to this statement right here. Now, if I were to stop right here, which my approximation does stop at, this would be p sub 3, a 3rd degree polynomial, plus the 4th derivative evaluated at some c value. Now remember, c is still between 0 and x, and that goes all the way back to here. When we did the mean value theorem, 0 and x were the a and b values, so c has to be between there. And this statement right here is a Lagrange error, and it's equal to all the remaining terms that I cut off, which is why my approximation for p sub 3 is not equal to the actual value. So this Lagrange error is equal to all the stuff, all the other terms that I'm cutting off. So you're going to want to write all this stuff down here. The error of a p sub 3 of x polynomial approximation is equal to all these other terms that I've cut off, and that in turn is equal to this right here. And you can see that just if you go up and down and compare them. And this statement right here is the actual Lagrange error. So a few more things for you to write down, pause as needed. So I can say that the 4th derivative of f evaluated at some value between 0 and x, evaluated at c, is equal to all the stuff at the end. And all the stuff at the end is this stuff right here, which means that the Lagrange error is equal to an infinite sum. Because remember, this statement right here is the Lagrange error. One thing to keep in mind here, remember in the last video we ended up with saying something about n plus 1, and I said that we would keep going with the n plus 1 idea. Right here, let's look at what we have. We had a polynomial p sub 3, and we noticed that the Lagrange error was the next term, the 4th. So if we have an nth degree polynomial, the Lagrange error, which is this statement right here, is going to be the n plus 1st term evaluated at c, which is a different place between 0 and x. It's not going to be evaluated at the centering point. It's evaluated at some point between 0 and x. Now the thing is, if I knew what c was, then I could actually find what this term is equal to, and then I could find what the error is exactly equal to. The thing is, you don't know what exactly c is, and the AP exam will never tell you what c is. So the whole point of an error bound is to give us the maximum that our error could be. And it tells us how far away we could be from the real answer. Because remember, the whole idea of error is telling you how far you are from an actual f value. So you have f of something, you approximate it with your polynomial of something. They're not going to be exactly the same. There's going to be some error involved. Your job is to find out a bound for the error, like an upper bound, like how big could the error be. It's to find the maximum our error can be, because that will tell us how far from the answer we are. So let me summarize that here. What I did here is I summarized the stuff I said above. So I want you to pause the video and jot this down. You're almost done with the notes. And once you have that written down, you can continue, and I have a couple more things I want you to write down. So here's the general form of a Lagrange error. The error is approximately equal to this right here. This is for a Maclaurin series whenever it's centered at 0, and you don't have to have x minus a, it's just x right there. However, if you want the more general definition, which is the one you'll be using more, this is when it's centered at x equals a. Notice the x minus a right there. It's the same exact thing. Now notice right here I put less than or equal to, because this is a bound. Sometimes they're going to ask you what's the largest that the Lagrange error bound can be, or you're going to have to find a bound for it. So this, you can either have approximately equal to or less than or equal to. Depends on how the question's worded. Now, again, I know all this stuff seems complicated, but when you do it on a free response, we don't have to make it more complicated than it is. All you have to do is fill in this value right here in green. And this is, oh wait, I forgot something here. This is at C. Whoops. What I put in green here is the maximum value on the interval a to x. Before we had 0 to x, but we want to make this general on any interval up to x. This is all you have to do. Fill this in. You don't touch the factorial. You don't touch the x term here. Now, a couple of things to keep in mind about a Lagrange error bound. We never actually know the exact error. All we can do is approximate it with this Lagrange error bound. Another thing is the Lagrange error bound, because it's an approximation, it's always going to be way bigger than the true error. And we don't know what the true error is, but we're going to get as good as we can and just find the absolute maximum that the error could be. Another thing to keep in mind here is that the Lagrange error, this is always in the form of being the next term, like the n+1 term, just like we found right here. If it's p sub 3, the Lagrange error will be the fourth derivative at some c value between 0 and x. Another thing, sometimes you're going to have to show that it's less than a certain number, which is where this comes into play. And put a star around this one because this is really important. You estimate the remainder by using the largest possible value that this can be for any c in 0 to x, which is why I put maximum right here. So pause and get all those notes down so we don't have to write them in class and you already have it. Now, if you're confused about any of this, which I'm sure some of this is a little bit intimidating, we're going to go through it, explain how it's applied in free responses. Last thing I want you to write down, which is what we're going to actually do in class, is on the free response, it's pretty predictable how they're going to ask a Lagrange question. It's always asked the same way. They're always going to tell you what this maximum value is. You just have to know how to dig through all the notation, because the notation is the worst part about this. The people who don't answer these on the free responses are the ones who get intimidated by the notation and don't understand how this works. If you remember these 4 things, then you can answer any Lagrange question. It's always going to be, you're going to tell you what the max is in one of the 4 ways. They're either going to have a Taylor series that involves sine and cosine, in which case the maximum is always 1, because if you think about a sine graph or a cosine graph, they're the same thing, just shifted. It always goes up to 1. It goes down to -1, but the maximum is going to be 1. They might just flat out tell you what the maximum is. You might have to get the maximum from a graph, and you might have to get the maximum from a table. Keep in mind, all we care about is replacing this piece, which is right here, with that maximum value. You're going to keep everything else the same, and then you're going to manipulate it a little bit. But if you remember, you're just going to replace this with what the maximum is, then it's going to seem a whole lot easier. All right, so I'm going to stop here. Bring all those free response slips that we did last week in class, because we're going to go and tackle all the error problems that we left out last week because we just did the series parts. And I'll see you in class tomorrow or Thursday. Bye.